Good morning. I'm here to present P2T Transport, a protocol designed by me, Fadi, and by my supervisor, Claudio. P2T Transport is a protocol to remotely exchange physical products between a customer and a merchant. It's a protocol which aims to solve a basic but very common scenario where a customer buys an item from a merchant remotely, and then he wants a transporter to bring it close to him. We obviously have already solution for this problem, so why create another one? Well, today's e-commerce has some problem. For example, the merchant needs all the customer's data in order to process a payment. For example, a merchant needs the identity, the payment options, and the physical address of the customer. Then the merchant will share at least the physical address of the customer in order for the transporter to deliver the item. Finally, for each payment there is a receipt. A receipt links a customer to a merchant and the transporter. The consequence is that there is no privacy. Sensible customer data is shared between the merchant and the transporter. This data is stored in centralized places, and as we know, this data can be sold or can be stolen by other people. There are some proposals which use the blockchain in order to solve these problems, but they have some kind of problem on their own. For example, some protocols use GPS devices, which are some kind of oracles. Therefore, you need to trust these oracles, and therefore these protocols are not trustless. Other protocols use deposits or collateral. For example, when the merchant has to put a collateral, so that if the merchant is a bad actor, he will be punished keeping out his collateral. Other protocols need strong capabilities of the blockchain. For example, they need some smart contract to recall other smart contracts. Those kind of things are possible on some blockchains, but not on the other. To solve these problems, we want P2T Transport to have some properties. Among those properties, we want P2T Transport not to require collateral. We want P2T Transport to be atomic, so that no party involved can lose money or the product if other parties misbehave. We want trustlessness, so that no party has to trust the others. We also want P2T Transport to be private for the customer, so we never ask sensible data about the customer. We also want plausible deniability, which means that no party but the merchant, the customer, and the transporter can be certain or can prove that a payment has been made. This is different from today because, for example, the email provider of C can read C's email and see that C has bought something in a marketplace. In our protocol, we make two assumptions. The first one is that in-person communication is secure under active attacks. For example, passwords can be heard or overheard, but they cannot be changed at the moment when one party is speaking to the other. Also, we require that all devices are secure and that nobody tampered with them. To explain pay-to-transport, we use the following notation. We say that the merchant is M, the customer is C, and the transporter is T. We use delta PQ for two parties P and Q as an estimate of the time that T needs to go from the pickup point of party P to the pickup point of party Q. P and Q are two parties among M, C, and T. Also, generally, the time from P to Q is different from the time from Q to P. We also define epsilon t as the maximum time that T will wait before he returns the package to M in case the customer C doesn't go to his pickup point. Finally, we define delta T tilde as the sum of all the quantities said before. We define also two constructions to understand the protocol: derived blockchain addresses and conditional transactions. Any secret key on elliptic curve cryptography is just a number in the group ZP. Also, the public key is just a point in the elliptic curve. Therefore, given a label X, which will be our order, and a numerical representation of its hash, we can derive a secret key and call it SKX, and derive a public key from that derived secret key. From that derived public key, we can derive a derived address from A and X and call derived address of A and X. We will make payments to derived address only to preserve privacy of the real address of the parties. The second construction is conditional transactions. A conditional transaction is a transaction with more than one branch. So usually one branch is used before a certain time or a certain block, and the other branch is used after. Pay-to-transport has two kinds of conditional transaction. The first one is conditional transaction with secrets, where to redeem it you need to provide a secret. And then we have simple conditional transaction without secrets. More specifically, given two parties A and B, a value f and a time t, and a secret hi, we define a conditional transaction ABVTHI as a transaction which is redeemable by a multisig between party A and B if it's redeemed before time t, and the signature of only party A if it is redeemed after time t. Also, if I is equal to 1, then the secret is in the first branch of the transaction, so both parties A and B has to provide the secret. Instead, if I is equal to 2, then the secret is in the second branch of the transaction, so just party A alone has to provide it. Finally, some conditional transactions do not have any secret, and we denote them as ABVT null. When we say that party A can redeem the transaction, we actually mean that party A can spend this transaction using the derived secret key. Let's present the protocol. The protocol is divided in three main phases. In the first one, customer C just decides the item I and it starts the payment with merchant M. In the second phase, transporter T picks I from M and it takes to a pickup point chosen by C. In the third phase, there is the end of the protocol. Either C accepts the package, so the protocol is successful, or T returns the item to M, in case C refuses the package. We explain the protocol in more detail. In the following, we abuse the notation, and when I see that the payment is done to C, to M, or to T, I actually mean that the payment is done to a derived address of the party. In the first phase, C decides the item M and the merchant M. Then C and M engage T, the transporter. After engaging T, C accepts the transportation cost CT. After that, T generates a secret R and it computes its hash, capital R. Then T sends the capital R to C. Finally, C pays the transportation cost to M. This is the only transaction of this phase. The second phase involves conditional transactions. First, C sends the first conditional transaction CT1, where that transaction can be redeemed by a multisig of C and T before time T1 plus delta tilde, and it has the secret R in the first branch of the transaction. This means that to redeem this transaction, the multisig has to provide the secret. Also, note that the amount of the transaction is the whole cost of the item CI. After doing that, T has proof by seeing the blockchain that C has committed to pay T, even if T cannot redeem this money yet. So T does a second conditional transaction. In the second conditional transaction, T just proves M that he has somehow freezed some money. So this transaction is redeemable by T and M together before time T1 plus delta Tm. So the time that T needs to go to M. There is no secret in this conditional transaction. Then T goes to M and M gives the package to T. At the same time, T and M are together, so they redeem transaction C2 and they write transaction CT3, conditional transaction 3, and this transaction is redeemable by M and T, a multisig, before time T1 plus delta tilde plus delta, which means that it is redeemable after the time needed to go to the pickup point of the customer and coming back. The secret in this transaction is put in the second branch, so M alone can redeem this transaction after this time only if she has the secret. Let's see the third phase in case the protocol is successful. If she accepts the package, then C and T can spend the first conditional transaction. Therefore, we have that T, by spending CT1, we release the secret R. Note that T received CI coins, while he spent CI minus CT. So by doing the summation of these two quantities, we have that T has CT coin more than before, which were the transportation costs. After T releases R, M spends the conditional transaction free, providing the secret R, which were in the second branch of the transaction. On the other hand, if C refuses the package, then T will have to bring the package back to M. Obviously, he has to do that before this time, so that both T and M can send money from CT3 to T's address. Note that in this case there is no secret needed, because the secret was in the second branch of this transaction. Also, note that in this unsuccessful case, T will not use any money, but he will have no coins more. So, in conclusion, we proposed a protocol to exchange goods remotely. We have worked mainly to ensure the privacy and pseudonymity of the client. These choices come at a cost. For example, C will spend the transportation cost even if he refuses the package I. This is actually needed to prevent C to spam the merchant M with a lot of requests with no intention to pay for them. We want to make spam costly. Also, T has to have money set aside for this kind of exchange. In fact, T has to provide the money before he has the money from C. Finally, M has a delayed payment because the merchant needs to wait for an amount of time before he can release the payments. On the other hand, we have some qualities in this protocol. The first one is atomicity. In fact, nobody can remain with both the money and the package. There is no way given the protocol. Also, C is both private and pseudo-anonymous. In fact, C will always use new addresses for new requests, so neither the merchant nor the transporter can know in advance who C is. The protocol is also trustless. In fact, no party has to trust any other party, because thanks to conditional transaction, if some party misbehaves, all parties can redeem their money. Thanks to derived addresses, all parties have plausible deniability. In fact, nobody on the blockchain will see the actual addresses and the actual transactions. Finally, we didn't use any smart contract to do this protocol. In fact, this protocol can be used on the Bitcoin blockchain and on the other more complex blockchains such as Ethereum or Tezos. Thank you for your attention.